Hello there. Last time we started off by talking about dynamic analysis of buildings, and so let me just continue. And we showed that if you have, in buildings, you have a situation where you could do two-dimensional analysis or three-dimensional analysis, and we showed that two-dimensional analysis can be done when the center of mass and the center of stiffness of the building coincide with each other, and that there are no should we say what are known as eccentricities in this structure. Okay. These kind of buildings are actually known also as symmetric, plan symmetric buildings, because the center of mass and the center of stiffness are coincide. So, this is called as plan symmetric buildings, and in plan symmetric buildings we saw that you did not have to consider the building as a whole. You can actually do what is known as 2D analysis, where you can consider each frame or all frames together. That is not a problem, because in one direction all the frames act together, and so you can do a two-dimensional analysis for the structure. Today what we are going to be looking at is what happens when you do not have plan symmetry. In other words, you have a situation where you have to do three-dimensional analysis of the building. Okay. Now, typically in such a situation, what advantage we take is we take advantage of the fact that typically in buildings, okay, the slab at every floor is considered to be rigid in plane. Okay. And in plane it is completely rigid, and a slab is completely flexible out of plane. So, in other words, once you have rigidity in plane, you can actually define the degrees of freedom in this fashion at any point. And typically what we do is we consider u x, u y and u theta, okay, defined at the center of mass. Okay. So, when you define it at the center of mass, what happens is that you can define these three, because in its plan, okay, every point is really defined in terms of these 3 degrees of freedom. So, let us take a situation where you have, well, let us assume that there are no beams and there is just columns. Okay. This is of course an approximation, but for now I do not want to make it too complicated, and we will see that you have a situation where I will say that this is the slab. So, in this direction and this is completely flexible out of plane, and this is completely rigid in plane. Okay. In plane it is completely rigid, okay, and this is typically what you assume, typical floor slab assumption, where it is considered to be completely rigid in plane and completely flexible out of plane. Okay. So, let us assume that in this particular direction, this is given by 2k. In other words, whichever direction it moves in, it is 2k, this is also 2k. So, this is 2k for movement in any direction, and these are square columns. So, in both directions they have the same, okay? And this one is k and k. Okay. So, if you look at it in this direction, okay, this is a and this is a thicker. Okay. So, if we look at it in this direction both of them have the same. In this direction, this is 2k and this is k. Okay. And this again is completely out of. So, you understand it's a one story frame. Okay. And these are our degrees of freedom, and let me assume for now, okay, that there is a, what shall we say? We will say that there is a ground motion. Let us assume ground motion given by V g of t, and this is V of x, sorry, V of y, V of x and V of theta. Okay. So, these are, so first and foremost, given this problem, what we need to do is we need to write down the equation of motion. How do we write down the equation of motion? Okay. Our degrees of freedom are given as follows. V is equal to V y, V x, V theta, and the ground motion is only along the x direction. So, what you have is you have V g x. So, there is only x direction. This thing. So, if I were to draw this, okay, it would be like this. Let me just draw this. And all of these are resting on the same raft. Okay. So, this is all resting on the same raft. This is x direction, this is the y direction, this is z direction. So, you have u x, u y, and you have, I am going to show this in a vectorial notation, sorry, v x, v y and v theta. Okay. So, this is, in other words, this is the rotation. The rotation is shown in right hand coordinate system in this direction. Okay. And this is 2k in any direction. These are all square k, and this is k and k. Okay. So, now, and what is happening is that this entire thing is being subjected to V g x of t, and this is the center of mass. Okay. So, now the thing that happens is, how do we write the equations of motion? Well, the way to write the equations of motion is to give each displacement quantity and find out what are the forces executed by this. And so, for that I am going to do, what I am going to do is I am going to show everything in plane. Okay. So, and let us also say that this is B B and this is from the center A A, and the center is right at the center. Okay. So, it is right at the center of mass. Okay. So, this is B and B, and this is A and A. Okay. So, if I look at it in plan and I give V y equals 1, what happens? This goes this way 1. Okay. So, what happens is, because of this displacement, this force is set up as 2k, this force as 2k, this force is set up as k, and this force is set up as k. Okay. And what we have here is also m into the acceleration. Okay. So, what we have now is, having put it this way, then what let us do? Let us put x direction. So, if I have x direction displacement, I have this way. Okay. So, I have, again, since it is gone in this direction, I will get 2k here, I will get 2k here, I will get k here, and I will get k here. Okay. And finally, what we need to do is look at, this is V x equal to 1, and the final thing is V theta equal to 1. And if I look at this, again, please note that this is small displacement. So, if I give theta here, what happens? If I look at this, okay, this part, if this theta is 1, then this will move by b, this will move by b this way. And what about this one? This one will also go this way 1. So, this will move by a and this will move by a. So, if that is what happens, okay, if you really look at it, this is what happens. So, this point goes this way, this point goes this way. So, if you look at this point has gone this way and this way. Okay. This point has gone this way and this way. So, you essentially, if I draw it in blue, this is the kind of displacement pattern. I will draw all the displacements patterns in blue. So, here see, so this point goes here. Let us look at this point. This point goes here and up. So, it is here, and this point goes down and to the right. So, it comes here. So, if you look at it, the displacement pattern looks like this. Now, this may look huge, but note that this is small displacement. So, in other words, this point has gone this way by A and this way by B. Okay. So, that is the fundamental point that we have. So, therefore, if I were to draw it, okay, since this has gone this way by B, okay, so at this point I have 2bk here upwards. Since this has gone this way, it will also have a force here, and that is equal to A into 2k. So, 2ak. Similarly, this one, since it has gone up, it will be coming down, and this is equal to 2bk. And similarly, since it has gone this way, it will come this way, and this is 2ak. Similarly, this one, since it has gone this way, it will go down this way, and that is equal to a k. This has gone this way, so this will go this way, and it will be b k. Similarly, since this has gone this way, okay, it's gone this way, so it will have a force in this direction equal to a k, and since it's gone up, it will have a of b k. Okay. So, these are all the forces that we have. Okay. And for us to find these out, all we need to do is just find out the forces at this point corresponding to these. The only problem is when you have cross. Okay. So, what we need to do is These are the forces undergoing these displacements. That is how I find out K12. So, let us find out first K11. K11 is what? It's in the y direction. So, what you have is all the forces undergoing this. So, you have nothing but K11 is essentially 2 plus 2 K plus K 6 K. Okay. Let us look at K22. 22 is what? K22 is going to be, give this displacement, there is a virtual displacement is also this. So, it will become equal to 2 plus 2 6 K. K33, give it a rotational virtual rotation, and so and find out how much work is undergone. Okay. So, this is going to be equal to 2 b squared. So, it is going to be 2 b squared k, that is for this. Then for this it is going to be equal to 2 a squared k. So, it is going to be 2 a squared k. Then you are going to have b into this thing. So, this is going to be b squared k plus a squared k plus a squared k plus b squared k plus 2 b squared k plus 2 a squared k. So, if you add all of those, if you look at it, 2 plus 1 3 plus 1 4 plus 2 6. So, this becomes equal to 6, and let us look at A, 2 plus 1 3 plus 4 plus 2 6. So, I will put 6 k outside, and inside I get a squared plus b squared. Okay. So, this is my K112. Let us now find out K12. K12 is what? The force at 1 due to displacement at 2. So, for 1 2 the displacement is at 2. So, this is the real one, and this undergoes this displacement. So, let us find out what is the work done. All the forces are in this direction, displacement is in this direction, work done is 0. Similarly, let us look at K13. 13 is what? Force displacement is 3. So, this is the displacement 3, and force at 2 corresponding to this. So, let us find out all the forces that are acting in this direction, 2 bk, bk and bk and 2 bk. So, this is 0. Okay. So, that is the work done. Okay. Because if I make this undergo in this direction, these will do one direction work, these will do opposite direction work. So, it is equal to 0. Now, let us look at, so I have done K13. So, let us now do K21. K21 is obviously it has to be 0, but let us see, this is this one undergoing this displacement. Okay. So, the work done is automatically 0. K22, so it is done. K23. Let us look at K23. 23 is what? These forces undergoing this displacement. Okay. So, let us look at it. So, that means this one is being, these are the forces which are being subjected to displacement in this direction. So, the work done will be, if I put, so the work done will be, this thing is in this direction. Okay. So, the work done will be 2 k plus 2 k, 4 a k minus 2 a k. So, it is going to be minus, it is 4 a k minus 2 a k, because this is doing positive work, this is doing negative work. So, in k it becomes negative. So, this becomes plus 2 a k. Now, let us look at K32. 32 is what? These forces undergoing this displacement. So, let us look at it. All of them are in this direction. So, let us just find out what is the work done. All of them are A, Okay, so it's A in this direction. So this one does a negative work, right? This one does negative work. This one does positive work. This one does positive work. Okay, so that means this is negative and this is positive, and then minus of that. So this becomes then what? 2ak plus 2ak. So it becomes 2ak plus 2ak minus ak, which is equal to 2ak. Well, symmetric, obviously has to be symmetric. So we've got our stiffness matrix, and the stiffness matrix is what? Stiffness matrix looks like this: 6k 0 0, obviously 0 0 here, 6k, okay, 2ak, 2ak, and this one is 6k a squared plus b squared. That's my stiffness matrix for the degrees of freedom, uy. These are corresponding to vx, sorry, vy, vx, v theta. Okay. Now let's look at the mass matrix. The mass matrix, since the degrees of freedom are defined at the center of mass, the mass matrix is very, very simple. The mass matrix is equal to the linear mass 0 0 0 m 0 0 0, and the mass moment of inertia. The mass moment of inertia, I am not going to derive this, I have already derived it for the linear term. It's equal to this. Remember, I have done ml squared by 12. Okay. So this one also turns out to be that. Okay. So I have my this thing. Now the question becomes, okay, what is my this? So now on the opposite side, I have uv, this u. So now this is again corresponding to vy, vx, and v theta. Now if you are looking at the loading vector P, this is going to be equal to minus m into, now we need to see the M matrix is this one, multiplied by, now let us see what it should be. What is the displacement in this thing? This is 0, and this is v double dot gx, and corresponding to this is 0. Okay, so this is what the P looks like. So if you look at it, this becomes then equal to what? Well, let us see. This is then equal to the following: m into v double dot plus k into v is equal to minus m into 0 v double dot gx 0. Okay? And this mass matrix, the mass matrix is diagonal m m m a squared plus b squared upon 12. Okay? Then I will call this as v y, v x, v theta plus k is 6k 0 0 0 0, 6k 2ak 2ak, and 6k a squared plus b squared, okay, into vx, sorry, this is not this thing, this is vy, vx, v theta is equal to minus m. So if we look at this, if you look at this, this into this basically becomes just 0, m Vgx 0. Now, if I look at the first top equation, what does the top equation give me? M V double dot plus 6k Vy is equal to 0. This implies, and this is of course with this thing, this implies that this is equal to 0, and we do not even need to consider that. So, then essentially this 3 degree of freedom for this kind of loading becomes what? It becomes equal to the following. It becomes equal to a 2 degree of freedom problem, which is m 0 0 m a squared plus b squared upon 12 v x double dot v theta double dot plus 6k 2ak 6k into a squared plus b squared Vx v theta is equal to minus m Vgx 0. Now, note, it is because of this, that 2ak into v theta, that you have coupling. So, essentially although Vy is equal to 0, both Vx and Vx and v theta are not equal to 0 because of this coupling term. If there was no coupling, if this was 0, then note that you would get them as separate terms, and you would get that as a completely separate problem. Okay? So, now if we look at it, and I am going to define your a squared plus b squared upon 12 by r squared, where r is the mass radius of gyration. Okay. So, then this becomes mr squared. Okay. So, the whole problem then it becomes mr squared, and what we are going to do is do the following. Okay. It does not matter. Let us just go ahead and do it. So, it becomes m 0 0 mr squared Vx v theta plus 6k 2ak 6k, now a squared. So, this becomes essentially 72 kr squared, 72 kr squared into Vx v theta is equal to minus m v 0. Now, let us say that I have defined, instead of defining v double. So, this becomes my equation of motion, where r squared is given in by this term. So, this becomes my equation, and the advantage of this equation is that it is 2 degrees of freedom, and with the only load and 1 and 0 for the other. So, what actually happens is, if you really look at it, this problem is actually a 2 degree of freedom problem. And I say that, look, in this particular case, I am giving the fact that is defined by SA So, response spectrum. So, I am going to do a response spectrum analysis. And let us, rather than put in these values of this thing, etc., let us just assume certain parameters. Okay. So, now first and foremost, if I am defined by this thing, I have to do mode superposition, okay, mode superposition method, okay, and let me define certain parameters. Let me define the parameter in this fashion. I will define a parameter delta, which I will say is equal to minus 2a upon r. Okay. So, no, sorry, it is not 2ak. Let us see. The way that is defined is it is 2ak upon 6k. So, that is a upon 3. So, this is going to be a upon 3r. Let me define this parameter by a upon 3r. Okay. And instead of Vx and V theta as my degrees of freedom, I am going to consider them as Vx and R V theta. So, this becomes an equivalent degree of freedom. Okay. So, now if I rewrite this, you will see this in this format. This will become m 0 0 m, okay, r v theta, okay. This will be 6 k, okay, minus delta into 6 k minus delta into 6 k. Okay. So, and over here I will call this as 72 k, because my r squared comes in here. This becomes Vx r v theta is equal to minus m v g x and 0. Okay. So, this becomes my new equation. You will see that this can be put together. Okay. Now, let's go ahead and look at this, try to solve this one. And let us assume another parameter. Another parameter that I will define is I will define omega x squared, and I will define omega x squared by 6 k upon m. Okay, I will explain. Later on we are just substituting to make it simpler. Okay. So, if I take m out and I take m out and I divide throughout by m, my whole equation becomes the following: 1 0 0 1 r v theta plus omega x squared minus delta omega x squared minus delta omega x squared, and this becomes 72 k upon m. So, this becomes 72 omega x squared. Sorry, 72 by 6. So, this becomes 12 x squared V x r v theta, and is equal to, now I am dividing throughout by m, so this also disappears. So, this becomes the equation. Okay. Now, this equation is, now I am going to, how am I going to solve this? I am going to use mode superposition. So, for mode superposition, I have to first solve the eigenvalue problem. So, let us look at what the eigenvalue problem is. The eigenvalue problem becomes omega x squared minus omega squared minus delta omega x squared minus delta omega x squared, and here I have 12 omega x squared minus omega squared, okay, into phi is equal to 0, 0. This is the eigenvalue free vibration problem. Okay. So, if I put this, that means the equation, my equation becomes this, omega x squared minus omega squared, 12 omega x squared minus omega squared, minus delta squared omega x fourth, okay, is equal to 0. So, now I have the first one becomes, so my equation, my frequency equation becomes the following. It becomes omega fourth, and then I have minus 12 minus, so this becomes minus 13 omega squared, and then I finally have omega x fourth. So, that is going to be equal to plus 12 minus delta squared x fourth is equal to 0. Now, I can actually divide throughout by x fourth. So, what I will get, I will divide throughout by x fourth. So, I get my equation as in this form. Where omega is equal to omega upon omega x. Okay. So, this is the equation. I have done all of this to kind of simplify the equation that I get, and this is just a quadratic in omega squared. So, omega squared turns out to be equal to minus b upon 2. So, that becomes 13 upon 2 plus or minus b squared 169 minus 4 minus this, okay, minus 4. What is 4? 48, sorry, 1 upon 2 here, minus 4, that is 48, a is 1. So, this becomes minus 48 plus 4 delta squared. So, this basically becomes 13 by 2 plus or minus half. This becomes equal to 121, right, plus 4 delta squared. And let us look at delta. Delta is what? Delta is equal to minus, let us look back at what we had defined it as, that was equal to minus a upon 3 r. What was r? R was a squared plus b squared upon 12. So, this becomes equal to minus 4a upon a squared plus b squared. This is what my delta is. Okay. So, now obviously, this one I cannot do anything about. Depending on a and a b squared, we can always find out what this is. But essentially, if you look at it, you will see 2 parameters. Okay. Suppose I put, let me put a equal to 1 and b equal to 1. Okay. What do I get? Sorry, a equal to 1 and b equal to 2 squared. Okay. So, you get here, you get 1 over here and this becomes 5. So, this becomes minus 0.8. Okay. And so, therefore, if you plug this in, delta becomes 0.8. If you plug this in, delta squared, this term is actually quite a small term. Okay. So, if you look at this, this basically I can neglect this, you know, and put this as equal to 11. Okay. Plus 2 delta squared. Okay. So, if you look at this, this in a sense half over here, it becomes, if you look at it, it just becomes nothing but 1 plus delta squared. So, if you look at it, this one becomes minus, if I take the minus 1, this becomes minus. So, it becomes 1 minus delta squared. So, omega 1 squared becomes 1 minus delta squared, and if you look at omega 2 squared, which is the addition one, okay, you get 22. So, you get 11, okay, 11 plus 11 by 2, 24. So, you get 12 plus delta squared. So, these if because delta is small, delta squared becomes small compared to this. Okay. So, you can say delta small. Okay. So, therefore, you get this kind of a term. Okay. Very, very interesting. 1 minus delta squared plus 1 minus delta squared, and you can just go ahead and do it and you will get it. Okay. So, essentially what we get is the following, and that is that you do not, so these become the omega 1 squared, and let us plug in these values to get the phis. Okay. So, let us plug in this value. So, we will see what we get. So, if I plug in to this, what was the original equation that we have? So, I have omega x squared, right. So, this is going to be equal to minus omega squared. So, this is omega 1. So, this becomes 1 minus. So, this becomes 1 minus delta squared omega x squared. The other one turns out to be delta omega x squared. Okay, this becomes minus delta omega x squared, and this one, if you look at it, it becomes 12 omega x squared minus 1 minus delta squared, okay, into omega x squared. And this one, if you look at it, this is phi 1 1 phi 2 1 equal to 0 0. Now, look at this, this becomes 0 and this is very small. So, this actually goes to 0, okay. Or you can actually say, well, it does not go to 0, it goes to delta squared omega x squared. Okay. But you see, if your delta is small, this term actually disappears. It is this equation that gives you the value. So, what you get is the following. You get the following, that this minus this upon this gives you. So, if you put phi 1 1, what is phi 1 1? Phi 1 1 is V x. So, you want to put that equal to 1. So, if you put that equal to 1, then the other term basically becomes this plus this. So, phi 2 1 becomes this upon this. So, essentially what you have is phi 1 becomes equal to 1 and the other one becomes delta upon 12 omega x squared and omega s squared cancel out 12 minus 1. So, that becomes 11 plus delta squared. That becomes your first term phi 1 1 and similarly you can get phi 1 2. Okay. The question then becomes is this, that let us assume, okay, what will happen is if you take this as alpha, you will see that phi 1 is equal to 1 alpha and phi 2 will be minus alpha 1, and since m is equal to 1 0 0 1, you will see that they satisfy the conditions, and what you get as m 1 is equal to 1 plus alpha squared and m 2 is also equal to 1 plus alpha squared, where alpha is equal to delta upon 11 plus delta squared. Okay. So, this is what you get as your expression. Okay. Now the question then becomes the following, and that is that okay, so we have got m 1 m 2, we have got phi 1 and phi 2, we have got omega 1 and omega 1 is 1 minus delta squared omega x squared, omega 2 is equal to 12 plus 2 delta squared omega x squared. Okay, so, these are the two frequencies, these are the m's, and so what you get is all you need to do is find out L 1, which is what? Which is equal to phi 1, which is 1 alpha, okay, into 1 mass into the r, which is equal to 1 0, right, because r theta is 0 and r the x is 0. So, this becomes then what? It becomes 1, this is a unit. So, this becomes 1 alpha. So, L 1 becomes equal to 1 and L 2, which is equal to minus alpha alpha 1 0 0 1 1 0 becomes equal to minus alpha. Okay. So, these are L 1 and L 2, and so therefore, L 1 upon m 1. So, if we look at this, what does y 1 turn out to be? Y 1 turns out to be equal to, let us see, y 1 is going to be equal to L 1. So, that is 1 upon m 1, L 1 upon L 1 into S d omega 1 into xi. Xi 2 is equal to minus alpha 1 plus alpha S d omega 2 into xi. And so, if we want to find out our term, and that term is I want to find out what V x and V theta are. Okay. So, this one into phi 1, right. So, that one, so in 1 is going to be equal to phi 1 y 1. So, that is going to be equal to, if you look at it, phi 1 is 1 alpha into y 1. So, that is 1 plus alpha squared S d 1. Okay. So, if you look at it, phi x 1 is equal to 1 upon 1 plus alpha squared S d 1, and V theta is equal to alpha upon 1 plus alpha. So, these are the peak values. These are the peak values. Similarly, if we find out the V x and V theta and 2, that is equal to phi 2 y 2. that is going to be equal to minus alpha 1, okay, into minus alpha into 1 upon alpha squared S d omega 2 psi. So, this becomes equal to V x 2 is equal to alpha squared upon 1 plus alpha squared into S d 2, whereas V theta 2 is equal to minus alpha into 1 plus alpha squared S d 2. Okay. So, now alpha values I have already put in. Okay. So, you know them. So, you can plug them in, okay, and that in essence becomes your fundamental concept over here, that V x 1 is equal to 1 upon 1 plus alpha S d 1, V theta 1 is equal to alpha into 1 plus alpha S d 2. Okay. And essentially you read off your sorry this is S d 1, okay. So, V theta 1. So, therefore, this is there. So, once you read these off, you can find out the displacement quantities given S d 1 and S d 2. So, and you know you can read off S d because you know omega 1 and omega 2, okay, and you can find out all of these. Okay. So, this in essence is what in a multi-storied building you have, you see you have actually rotations despite there being only a translational rotation, because there is lateral torsional coupling, and because of that coupling you have these kind of terms. And I have actually given an example problem to show you that how to go about it. Okay. So, now in essence what you have is that if you have asymmetry, in other words the center of mass and the center of stiffness do not coincide, you have to do a 3-dimensional analysis, and I just kind of went through the procedure of how a 3-dimensional analysis for a 1-story asymmetric plan building is to be done. So, I went through the entire steps, and this also in a way was kind of dealing with response spectrum analysis for a multi-story, for a multi-degree of freedom problem. Okay. I hope I have been able to give you an overview of multi-degree of freedom. First, you need to get the equations of motion. I have done that in this particular case. Next, you need to do the free vibration analysis. I have kind of done that. Okay. Third, you need to do the response analysis, and there are two ways to do response analysis. If you are given the time history of the load, you can do response time history, or else if you are given some form by which you can get the peak modal amplitude, you can use modal combination rules to get that. Of course, I have not applied the modal combination rules here. This in overview is dynamic response of multi-degree of freedom system problems. Thank you very much. From next lecture, I am going to start off on what is known as distributed parameter systems. Bye.